Last presentation we talked about the dynamic prefix sum problem, where we are given an array of n elements, where each entry of the array is an integer that can be represented by delta bits. Initially all the entries are set to 0, and then we were interested in a data structure that can support these two operations. In update operation, what you say is that set the kth entry of the array to delta, and this sum operation, this is the query operation. Here you are asked to return the sum of the first k entries of the array. Okay. Now, this lecture we will be concerned with a data structure that basically can answer these two queries. So, this is the verify sum query. This is slightly easier. It is given a number delta. It is asking whether the first k entries sum to delta or not. Okay. And we will see why this is interesting, to consider. We will see its connection to dynamic connectivity very soon.
So, integers are all positive integers?
For the time being, assume they are positive integers, and let's recall that I said the whole the whole proof works even if these entries are chosen from a group, where each element of the group can be expressed using delta bits. Okay. Now, each cell consists of w bits, and typically we will assume that this w is theta of log n, and the number of cells is polynomial in n. So, each cell address is also w bits. Okay. And what we did, we have said that okay, we can fix a specific permutation pi, and we can fix a tuple of elements delta 1 to delta n. So, that if we consider this sequence of operations, so from t equal to 1 to n, you first query what is the sum of pi t, and then you ask for this update. Okay. If you go through this sequence of query and update operations, then we showed that this will require, any data structure will have to make at least delta divided by w times n log n cell probes. And since the typical scenario is where delta is also log n, because the integers are polynomially bounded and w is log n, you get a lower bound of log n in the amortized sense. Okay. So, now today our main concern is this problem called dynamic connectivity. Let me first define the problem, and then we will see what is the connection between this verify sum query and this dynamic connectivity. So, here we are given an input graph consisting of n nodes, and the node set remains fixed, and initially the edge set is empty, and then you need a data structure that can support the following update operations. So, the insert operation just says insert this edge into the graph, delete operation says delete an edge from the graph, and then you have a query operation, and the query operation simply is u and v connected. Okay. So, we want a data structure that supports this update and query operation. Now, what we will show is, if we can prove a lower bound on the verify sum data structure, a data structure that supports these update operations and the verify sum queries, not the sum queries, okay, then we can prove a lower bound on dynamic connectivity. Okay. So, we will show this first, then we will go to the verify sum lower bound. The reduction is actually quite simple. So, what you do is, you build, since these two ends will be different, okay, I am now going to just let this be n star. This n star is different from this n. Okay. So, you build a root n star cross root n star grid of nodes. Okay. So, you are given this graph, you are just arranging them in a grid. That has root n star rows and root n star columns, the nodes of the graph. Okay. Now, what you do is, between each of these consecutive columns, you make a perfect matching. Okay. Something like this, and it goes on. Let us say this. Okay. Now, you can think of each perfect matching here as a permutation between root n, a permutation over this set of nodes, root n nodes, right, because this is a perfect matching. And let us call this first permutation by A1, this second permutation by A2, and this last permutation by A root n star. Okay. Now, just consider this array of these permutations. Now, you see where does this map into? This is the input, this is our input, the dynamic prefix sum. We will just set n to be root n star. The array A1 to n here is this array, and each entry in this array is a permutation over root n star elements. Okay. So, now let us just think in this setup what is delta. So, these are a set of permutations, right. So, these form a group, these permutations define a group under the usual composition operation. Okay. So, how many bits would you need to represent, uniquely represent one permutation? Okay. So, how many permutations are there? Root n star factorial, right. These many possible permutations are there. So, you will need these many bits to represent each permutation. Now, this is upper bounded by root n star factorial is definitely log of root n star to the power root n star, and this is root n star log n star. So, we have delta is root n star log n star. Okay. Now, when you ask for this update operation, it just says change the permutation AK to some other permutation. What you need to do? You will go to this AK and change this matching to a different perfect matching specified by this delta, and verify sum is sum of the first k permutations equals delta. What will this represent? You will, what will be the composition of the first k permutations? You will go to the, say this is the kth column, say this is the kth column, and this is the first column. So, this sum of the first k permutations, if you want to ask that okay, here is this node V, if I apply this permutation on this node, what will I get back? what you need to do, you just need to follow this path and see which node you are getting at in column K. Okay. Now, that is a connectivity query, right. So, when you are asking that if this permutation is equal to this permutation, what you need to do, you need to just apply root n star many connectivity queries. So, you will just look at this V and some other node here that is specified by this permutation and ask that if I start from V, will I end up in here. Okay. So, what we have is, let me just write it here because I will erase it anyway. Each update can be implemented using theta of root n star insert delete operations. And each verify sum can be implemented using again root n star many queries. Okay. Now, if we just plug in this lower bound for this instance of verify sum, suppose this lower bound holds for verify sum, we have shown it for sum, but suppose it holds for verify sum, what will it imply? The amortized lower bound for verify sum this is going to be omega of delta divided by W times log n. Now, let us plug in these values. What is delta? Delta is very huge, delta is root n star, right. So, root n star log n star. So, root n star log n star. W is log n, and here you have a log n. So, it just cancels out. So, you get root n star amortize, that is why I said amortize. So, okay. So, then what does this mean? The amortized lower bound for verify sum is root n star log n star, whereas what we have seen here is each update and verify sum operations can be implemented using root n star insert deletes and root n stars queries. So, what does this mean? For each insert delete and for each query, the lower bound becomes log n star, and then we are done, right, because this graph has n star nodes. Any question about this reduction? So, yeah, you will get a lower bound of log n. So, basically what we will what we can say then is there is a sequence of insert delete and query operations, n insert delete and query operations, such that any dynamic connectivity data structure will spend n star log n star time. So, you will get a lower bound of log n star on dynamic connectivity.
So, just a pedantic thing. So, here we shouldn't have this inequality because we are using a lower bound.
Which one?
The log of root n star factorial is less equal to, and that should be a theta argument, because we want it to be a lower bound.
Oh, no, no, no. So, what we can just say is that delta is at most this. This is fine, right? I mean, the number of bits you will need. So, I forgot what Stirling's approximation is for this. I mean, this might actually be theta. I mean, I think so. Yeah, so you can just say this is theta, fine. Okay. Yeah, let's just leave it like that. Okay. This is just one paragraph reduction. So, that is why this lecture we will focus on giving a lower bound for the verify sum data structure. Okay. So, now I forget everything about or erase everything about dynamic connectivity. Let me erase this one. Okay. Now, before proceeding, let us just wrap up one loose thread from yesterday's presentation, that of this interleaving number of a permutation. So, if you recall, suppose we had a permutation over n numbers from 1 to n. What was the interleaving number at an internal node? It was defined like this. So, let us just do this thing. Suppose this is 1, 2, let us just stop here. So, suppose you have a permutation over these 8 nodes, okay. So, there are 8 nodes. Let us just cook up some arbitrary permutations, say 2, 1, 8, 7, 6, 4, 3, 5. Okay. So, now the permutation is like that. This is the first node, first element, this is mapped to 2, the second element is mapped to 1. Okay. So, if you recall yesterday's presentation, if we fix this, so we are first building a complete binary tree on these n elements, and now if we fix an internal node V here, what is the interleaving number at V? You first need to look at its left ancestors, left descendants and right descendants, and now you just look at these 4 numbers, start from the lowest number 1, this is in the left subtree. The second lowest number 2, this is also in the left subtree. The third lowest number 7 in the right subtree. Fourth lowest number 8. So, the interleaving number is going to be 1, because you just crossed from left subtree to right subtree only once, and the same thing applies at every other internal node. Okay. So, in our earlier proof, we crucially needed one permutation that satisfies the property that the interleaving number at V is theta of, let us say, leaves at V, right. So, look at the number of leaves in the subtree rooted at V, the interleaving number is proportional to that. So, what we can easily show is, we can deterministically construct a permutation where this interleaving number is at least half times the number of leaves at each node. Okay. This is what we will show, how to construct such a permutation. Okay. So, how to construct such a permutation? Without writing down the formula, we can just see what is happening. The proof, formal proof will be by induction. So, if there are only 2 elements, okay, then this is the permutation, it has the interleaving number 1. Now, suppose there are 4 elements. So, you just make a copy of the initial permutation on 2 elements. Okay. So, this is 1, 2, 1, 2. Now we want a permutation over 4 elements. So what you do is you map this 1 to 1, this 2 to 3, this 1 to 2, 4. You see what is going on? I mean the number I here is getting mapped to 2i plus 1, whereas the number I here is getting mapped to 2i. And hence, since in this subtree the numbers are still distinct, right, 1 and 3. So the interleaving number in this node remains the same as before. In this node it remains the same as before. But in this node, the way you have done this, the first number is an odd number, it will be on the left subtree. The second number is an even number, it will be on the right subtree. The third number is an odd number, it will be on the left subtree, and it will be n over 2. Okay. And similarly, if you want to construct a permutation over 8 elements, what will you do? We will just take this permutation 1, 3, 2, 4, right. So 1, 3, 2, 4, 1, 3, 2, 4. And then how will you map them? This 1 will go to,
This will be 1.
yeah, 1 will be 1. Now 3 will be 7.
That one will become 5. No. It's basically you sort this and then stably sort this. And
Yes.
whatever
Okay.
the index number is, you rewrite it.
Yes, right. So you guys got the idea, right? So 3,
3 is not 5, 3 is 7. Oh, sorry.
no.
6. No, 5, 5, sorry. She's right. 5.
Yeah, 3 will be 5.
Yes. 3 is 5. Because there will be 2 1s and 2 2s before it.
Yeah, so okay, one way to visualize is this. The lowest number will be from the left subtree, and this is the lowest number. What will be the second lowest number? It got to be from the right subtree. So you make this thing to be 2. What will be the third lowest number? It has to be from the left subtree. So the third lowest number here is the second lowest number. So this 2 becomes 3. The fourth lowest number, it's from here. So this 2 will become 4. Fifth lowest number is from here. So this 3 will become 5. Sixth lowest number from here. So this becomes 6. Seventh lowest number from here, this becomes 7, and this becomes 8. You see what is happening, right? Okay. Now you can just write down the formula yourself, how to construct this thing.
It's called bit reversal.
Yeah, so the sequence, so that it's also called the bit reversal sequence for the following reason. What you can do is, let's just take a look at this thing, right? Say you just write down 1, 2, 3, 4, 5, 6, 7, 8. Now write down the bit representation for these things. Oh, I think you need to start from 0. Yeah, so instead of from 1 to 8, suppose you start from 0 to 7. Write down the bit representation of each of these numbers. Then just flip the bits in each of these places. Then the sequence that you will get will be the bit reversal sequence. So if you just want an example for a bit reversal sequence on the first 4 elements, it's going to be like this, say 0, 1, 2, 3. You want the bit reversal permutation. So write down 0 as 0, 0, this thing as 0, 1, this is 1, 0, this is 1, 1. Now flip the bits. So 0, 0 remains this, 0, 1 becomes 1, 0, this becomes 0, 1, this remains 1, 1. So now this is 0, this is 2, this is 1, this is 3. Now this is the permutation that you get, 0 to 0, 1 to 2, 2 to 1, 3 to 3. And you can just check that this is exactly what is happening here. Okay. Now we come to our main result. So all this is from chapter 3 of Nihai Patrasku's thesis. What is going on? Oh. Is this clearly visible in the camera? Okay. Okay. Verify sum. So, we need to show a reduction on verify sum, and as you can see, for the sum queries our update sequence was like this, right. I mean our input sequence were like this. For verify sum, I mean we need to come up with a different input sequence. This will not work because this query itself is not valid. Okay. So, before we proceed, let us introduce the notion of a non-deterministic cell probe data structure. And then we will see cell probe data structure. Okay. So, what is a cell probe data structure? In the last talk, we had this model. So, here are the memory. The memory is partitioned into cells. Each cell is W bits long. And I said there is an algorithm, Turing machine, whatever you think, that is sitting up here. After each update and query, it makes some reads and writes operations on this memory. Now, you can also think of this as a decision tree. So, how would the decision tree look like? After an update operation is coming, for the time being, yeah, suppose this update operation comes, you start from the root of the decision tree, say this is the root. Now, depending on the different update operations, how many different update operations can there be? You can just check. I mean, there are 2 to the power delta possible values of this delta, and there are n possible values of this k. So, this guy will have n times 2 to the power delta children. Now, at each of this node, suppose you fix one specific update operation. So, you came here. What will you do? It is defined that okay, now we are going to read a particular memory cell or write into a particular memory cell. What can be the outcome of that operation and how many children can this node have? Anyone? No, not n minus 1, it is simply 2 to the power w. Why? Because here you are just accessing one cell, right. So, what you are seeing here can just take 2 to the power w possible values. So, this will have 2 to the power w children, and when you have gone to one of these children, you have potentially performed some read and writes here in one of these cells, and then it goes on. Each of these cells have 2 to the power w children and so on. And the number of probes that you make, what is it going to be? It is simply going to be the depth of the tree, because as you go down one level, you are making one probe. So, this is an alternate way of viewing what is going on in a cell probe data structure. Now, this is deterministic cell probe data structure. What is a non-deterministic cell probe data structure?
So, in a node which is a read node, it has to cut away children.
Yes.
But why does a write node have?
No, I stand corrected. If it was a write node, it will have one child. If it will have one child. Okay. Okay. Now, what is a non-deterministic cell probe data structure? It is very similar to a non-deterministic Turing machine, or say non-deterministic finite automata. So, what happens is once you get an update or a query operation, just from the root you just create multiple parallel threads. Okay, this is not the root, just create many parallel threads. Okay. And then in each of these threads, you are running a deterministic cell probe data structure. Okay. And they are simultaneously making read writes, I mean in parallel in different threads. Okay. After some time, you can just think of that in the very beginning, each of these parallel threads has a copy of this memory and they are just working on its own copy. Okay. Then after a while, what will happen is only one of these cells will accept and the others, only one of these threads will accept and the others will reject. Everything else is reject. Now you just wipe out what the reject threads did with the memory and you just take the thread that accepted. So this accept thread, this made some changes in the memory, right? So that will only survive. So when the next update operation comes, the state of the memory is defined by what was done with it by this accept thread. This is just a very natural analog of say non-deterministic automata, non-deterministic Turing machines and so on. Okay. And the cell probe complexity of this non-deterministic data structure will be given by the number of cell probes made by this accept thread only. So regardless of how many cell probes these rejected thread makes, they do not count. Okay. Okay. Now, why does this thing matter? It matters because of this lemma. Mm-hmm. No, okay, yes. So here the restriction is that there will be exactly one accept. Okay. Because it is dynamic, because when you go to the next update, you need to define what your memory state is. If there are multiple accepting threads, there will be a conflict, right? I mean, each of them has resulted in a different memory state. Arjun?
So if it happens, then you choose one of them. First one.
Okay. Now,
cell probes, so maybe the number of cell probes are different in both the acceptance.
yeah, maybe there is a way of defining it like that. I cannot say that whether this will work or not work, but let us go with this definition. Okay. There will be only one accept threads. Okay. So the point is, why do we need this definition of non-deterministic cell probe data structure? It is because suppose we prove suppose there is an algorithm with cell probe complexity something, okay, data structure with cell probe complexity C for verify sum. Then there is a non-deterministic cell probe data structure with cell probe complexity C for sum. This is the reason we are interested in this. So the lemma is, if there is a deterministic data structure with cell probe complexity C for verify sum, then there is a non-deterministic with same complexity for sum. Now you can see why this is true, right? Because suppose you want to simulate this data structure with the sum queries. So when a sum query comes, you are just going to run n different verify sum, no, not n different, 2 to the power delta different verify sum queries in parallel. for each possible value of delta, and then only one of them accepts because the sum is exactly equal to one of those values, and the number of operations cell probes that you did corresponds to the number of cell probes in the accepting thread, which corresponds to the deterministic data structure for verify sum. Okay. So, basically to prove a lower bound on verify sum, we need to prove exactly the same lower bound on a non-deterministic data structure for sum. Is this clear? So, for the rest of the talk, we will be talking about non-deterministic data structure for sum. Okay, so let me just erase this thing. So, to prove a non-deterministic lower bound, let us first recall what happened with the deterministic lower bound. Crucially, we had this picture, right, that from yesterday's, from last week's talk. Look at this. Okay, before we proceed, to prove a non-deterministic lower bound on sum, we will use the same input sequence, exactly the same input sequence. Okay. Now, let us just review the proof and see where it goes wrong. Okay. So, on this axis was time, on this axis was the rank of the update. So, now you had multiple such points like this, where if you look at any particular point, this thing was t, this coordinate was pi t, and this point denoted the update here, update and the query here of so this coordinate was t comma pi t, and this point referred to this update, these two queries and updates. Okay. Then what we said was, on this axis, let us just erase these two things. On the time axis, since there were n possible queries starting from 1, 2 and t going to n, you build a complete binary tree on this side, like this, and say this is the root, and then at any internal node of this tree, let us define the interleaving number as the information transfer. We defined a thing called the information transfer, and it was as follows, that look at the left child of V, let this be LV, let us call this thing T1 of V, forget it. Okay. So, what was the information transfer? Look at this interval. So, this ends at T2, this thing begins at T1, this is T0, this is T1 minus 1. And now, what was the information transfer? Corresponding to this node V, it was set of cells that are read at some time t in this interval, that were written at some time t w in this interval. So, this is t w, T0 to T1. And not written during the intervening period. Okay. And then there were a sequence of lemmas. So, the first lemma was that the number of cell probes is bounded from below by the sum of the size of the information transfers at all the internal nodes. Sorry. Now, why was this the case? Because every cell read was counted exactly once, sorry, at most once in this sum, right? That was the first part. The second part was that lemma 2 was that there exists a permutation pi such that this size of this information transfer is at least half times the number of leads, which we just showed. Then from lemma 1 and lemma 2, we had lemma 3. No, sorry, I take it back. This is not information transfer, this is the interleaving number, okay. This just depends on the permutation, okay. And lemma 3 was a crucial lemma. It basically said that for all internal node V, this thing holds, W times IT of V greater than or equal to delta times IL of V. And this used an encoding proof that if you want to find out if okay, I will come to the encoding proof later on. This uses an encoding proof. We will recall what the encoding proof was in just a moment. And finally, lemma 1, 2, 3, they together implied, what did they imply? If you just sum over these cell probes, it is going to be sum over the information transfer, which is going to be delta over W times sum over the interleaving numbers. So, lemma 1, 2, 3, they together implied that the number of cell probes is going to be sum over this information transfer, which is greater than delta over W times sum over this interleaving number, and this is going to be this was the proof. Now, we will see that this lemma 3 breaks down for non-deterministic data structure, and we need to fix it. Why does lemma 3 break down? How did this proof work? Let me just draw this picture again. Because we will need it. So, fix T0, T1, T2. What we said was that just look at the points that lie within this slab between T0 and T2, and then just plot them in increasing order of their rank. So this is the rank, right? So these are the first few with the lowest rank, then you go to the larger ranks. Like this. And so the interleaving number was the number of times you were switching from the top slab to the bottom slab. And maybe here again you are switching, so on. Okay. Now what was the encoding argument? The encoding argument was, suppose you have two parties, Alice and Bob. They both know what the updates were in this slab, in this slab. They both know where the updates were in this slab, and they both knows the non-spatial updates within the slab from T0 to T1. And what were the spatial updates? The spatial updates were this. I mean the updates in this slab that just contribute to the interleaving number. So these are the spatial updates here. So if Alice only knew the spatial updates, what exactly this delta T was, then she can encode them using these many bits and send them to Bob, and Bob can run a decoding algorithm and recover these bits. And what was the encoding and the decoding procedure? The encoding and the decoding procedure was simply look at the cells in the information transfer, look at the contents of those cells just prior to T1 and send the addresses of those cells and the contents of those cells to Bob. And how many bits would you need? For each cell in the information transfer, you will need W bits for its content and W bits for its address. So this was basically 2W. Okay. And then Bob can simulate the data structure and thereby know what the output of the queries were at each of these updates during this slab, and from them the Bob can recover what the updates were here. Okay. Now what will go wrong if you are a determinist, if you are going to work with a non-deterministic data structure? What goes wrong in this proof? No, you can see that we are running all the threads. So the non-deterministic data structure is defined, right? The number of threads that will appear is also given. So what does simulating a non-deterministic data structure mean?
So when you cut it at that point, you need to send so many bits, not just one.
Yeah, so the point is that if, okay, so first of all, let us go step by step. First, how do you define the information transfer on a non-deterministic data structure? This has to be defined, this must be defined with respect to the accepting thread, right? Because during the update operations, we do not need different threads here. It is only during the query operations that we need different threads. But the number of cell probes is defined with respect to the accepting thread. So the information transfer here just consists of the set of cells written by Alice in an accepting thread during this lab and read by, sorry, not written by Alice, written by the data structure in this lab and read by the data structure in this lab. also in an accepting thread. Okay. Now, what is going to happen if Alice just returns these contents of those information transfer cells and their addresses? When Bob is simulating the data structure in this range, Bob has to run all the different threads. Now, when Bob's accepting thread wants to access a cell, Bob can do so using this information transfer. But it might be the case that Bob's rejecting cell wants to access and modify, rejecting thread wants to access and modify some cell, but that is not present in this information transfer. So, Bob gets wrong information about the contents of that cell, and that rejecting thread completely goes haywire. It does not know what it is going to do. I mean, it does something.
The worst case it could accept.
Yeah, it could also accept. Yeah, and then Bob does not know what is going on, right. So, the main problem is that how is Bob going to simulate the rejecting thread, because Bob does not know in advance which threads will going to are going to be rejecting. Okay. Okay. Now, the solution to that thing is, suppose somehow this thing does not work actually, but let us just consider this. Suppose somehow Alice sends the contents of the information transfer and also explicitly specifies the cells that are read by accepting threads. Okay. Then Bob can decode. Why? Because when Bob's rejecting thread wants to read a cell, he can just check from the list provided by Alice, and it does not match the list. It means that it is not an accepting thread, because Alice is saying that okay, I am giving you the list of cells that are being read by the accepting thread. Okay. So, basically you can see the following thing. Okay. Let us say these are the cells T0 to T1 that are read by the accepting thread during this lab interval. And let us say these are the cells that are written by the accepting thread during the interval T1 from T2. Now, what is the information transfer? The information transfer is simply the intersection. Sorry, I take it back. This is read and this is written. Okay. Now, this part is the information transfer. Now, can you tell me where does these cells belong to? These cells were not modified at all during the interval T0 to T1, and these cells might be read by an accepting thread. Okay. In T1 to T2, but a rejecting thread in T1 to T2 might attempt to read one of these cells, and that is the that is a case for concern, correct. So, if we could somehow specify these cells and Alice can transfer this information to Bob, then Bob can simulate the whole thing, right? Because Bob will run all the threads in parallel, and whenever it sees that in one thread is asking to read a cell from here, Bob will say, hey, this is a rejecting thread. Okay. So the point is that in addition to the information transfer, we need to convey the information about these cells.
What if rejecting thread
Mhm.
doesn't read from anything from here, but only from this intersection?
From this intersection? Yeah.
It doesn't read from that.
Yeah, this is fine, right?
Its history is different.
Sorry?
I mean, this is a rejecting thread. I mean, I have this decision tree. I'm accepting
Hmm.
that not deterministic
Mhm.
tree. My rejecting thread is a totally different history, but it wants to read something and it gets from this.
From this you are saying?
Yeah.
Okay, so suppose a rejecting thread, you are considering this situation, a rejecting thread in this interval
Right. Reads from this.
wants to read from this.
Its history is actually different, so it should get a different value. But here Bob uses this value. So doesn't that also go okay?
No, that works, right? Because when was this last updated? It was updated before T0.
Okay, no, from the intersections. Before T1.
From here,
Yeah, it reads from this.
then it reads the correct value because it is part of the information transfer.
No,
No, you told that you don't update the memory for the rejecting threads.
Yes,
So Alice is only sending the values of the memory during
Yes.
the accepting thing.
yes.
So Bob doesn't know the rejecting threads.
No, so okay, here is one clarification. Forget about Alice and Bob. What is going on in a non-deterministic data structure? After each update and after one update and query, you are running many threads. One thread accepts, the other one rejects. Once reject, you just erase whatever happened with the rejecting threads. And now the status of the memory after this update is given by the accepting thread. So when the next update and query comes, there will again be many threads, but they will just pick up the state of the memory from the previous accepting thread.
It reads the same. They are the same.
Yes.
So, right.
Okay, you start after you accept, you branch from that point, from the accept.
Yeah, or you can visualize it like this, that you created multiple threads, each thread had its own copy of the memory to begin with. They does something, each of them does something with this thing. Then one of them accepts, you just wipe out whatever happened in the other threads, just look at this thread and this is now your memory. After, mhm.
It's a decision tree where only one of them has a children, the remaining will stop having children. Right?
Yeah, so the decision tree is okay. So the thing is that after each update and query, you start again from the root. So the decision tree does not, cover multiple updates. A decision tree is only for one update. Or you can say that each thread is its own decision tree. Each thread is a decision tree. You can just think of it like this. Does it make sense? Okay. So then the point is, if you look at these special updates, we had this terminology, right? These are the special updates. And now Alice wants to send some encoding and Bob wants to decode that and get what the values of these delta t's were at these special updates. The thing is, as long as Bob knows the contents of the information transfer and the prohibited cells, meaning the cells that were written during the previous interval, but not part of the information transfer, meaning these cells are not meant to be read by the accepting thread. As long as Bob knows this list, Bob can just simulate what is going to happen in the interval T1 to T2. Okay.
So this,
Hmm?
so the model will say, this model says that it should be wiped out after one update.
Yes.
So this worked because we were, okay, so I had thought that this was a special property of the non-deterministic machine that we built. So So
No, that is in the model. That is part of the model. Okay. Okay. So now the point is, how is Alice going to send this information? Okay. One crude way of doing this is to say that Alice will just list all these cells here, but that is really inefficient. Why? Because specifying the address of a cell requires W bits. So, this will require W times capital W of T0 comma T1, and that is going to be too much, because if you just look at this sum, I mean ultimately you want to sum over all the nodes V, and how much you are sending for this particular node, it is W times this read, right, this write size of this thing. Now, you can see that this quantity, if you sum them over all the V's, it is really going to, I mean each write is counted log n times in this sum, right. If you just look at this, this is the cell writes during this interval T0 to T1. This is not like information transfer, which is counted only once if you sum over all the internal nodes. So, this entire calculation will just go haywire. I mean, then on the left hand side, here you are getting the number of cell probes equal to this only because in this information transfer, if you sum over all the internal nodes, each write counts once. Here each write will be counted log n times. So, you will get log n on both sides of the inequality, they will cancel out. Okay. Instead, what Alice will do is, Alice will just send these many bits of information. How? Bits of information Alice will send, and Bob will be able to decode these cells using these many bits. How? We will just show next, but before that let us see that this suffices, okay. That if we do not have this W factor in here, this suffices. So, how will lemma 3 change this encoding proof? The lemma 3 will change like this. Let me just write it. For all internal nodes V, Alice is sending W times the information transfer at V plus, let us just call this TV, so that this is well defined for each, sorry again TV. Sorry. And these many bits suffice to decode the values of the special updates. So, this is the interleaving number. So, this will be our new lemma. Suppose this lemma is true, then how can we derive this bound? Basically, you just sum over all the nodes, sum lemma 3 okay. What is this term? This term is going to be at least sorry, at most the number of cell probes, right? Okay, let me just write it down, okay. W times V such that IT of V plus V read and this is greater than delta times the interleaving number of v summed over all v. This is definitely delta times n log n. Okay, correct. Now what is this term? This term by definition is at most the number of cell probes, right? So we can just say W times, let us say T be the total number of cell probes. Okay, so W times T is greater than the first term. Okay, now what is this second term? This second term says, look at each internal node V, look at its one subtree, look at the number of writes that occur in this subtree. Now you are summing over all the internal nodes. So each write contributes log n times, one for each internal node to the root, up to the root. Okay. So this is going to be at least log n times t. This upper bounds this term. Okay. And similarly, this thing upper bounds this term log n times t. Okay. No, log n times t. See, what is this term? Can you just see what is this term? This term just says look at one internal node V. Look at, let's just look at this term T0 to T1, right? Fix any internal node V here. Look at the number of writes that occurred here. So if you sum over this quantity of W over all the internal nodes at the same level, what will you get? The total number of writes. Why do you think it's n? Total number of reads plus writes. Okay. For your convenience, let's just take these two terms together. Okay. Take these two terms together. Now, can you see that these two terms, sum over these two terms is exactly equal to log n times t. Why? No, not exactly equal to log n times t, should I say that? Upper bounded by log n times t. It is order log n times t. Now, why is this the case? It just says that if you fix one internal node V, what is these two terms? These two terms are the writes written in this interval and reads in this interval. So, this is less than the total number of read writes in this interval. So, if you sum over all the internal nodes at the same level, you basically get the total number of read writes, and now there are log n different levels. So, this is clear, right? This is Wt plus log n times t is at least this, and now you just use the fact that W is equal to log n. So, then what do you get? These two, if you just combine these two inequalities together, you get 2W times t greater than delta n log n. Okay. So, again you get the same bound. So, now the last part, the last 10 or 15 minutes, how can Alice do this thing using these many bits? Okay. So, basically this problem, let me just erase this part. Let us say U be the universe of all cells. This is a set. Okay. Now, think of this communication game. Here is Alice, here is Bob. Now, both of them knows this universe U. and they can communicate beforehand what communication protocol to use. Now, you specify to Alice two subsets W T0 T1. These are the subsets that we care about, okay? W T0 T1. Let us say this. So, by W prime T0 T1 I just mean this part, okay? That is part of W T0 T1, but not part of information transfer, and this part R prime, and so these are mutually disjoint, okay? So, now what happens is some adversary just specifies these two subsets to Alice and then says you can communicate something to Bob, some string x, Bob can receive this string, and after that Bob should be able to build a data structure that can output the following, that can answer the following query. What is the query? Not this, let us say S, okay. So, the S is an element of this universe, and it says that output a bit, right? This is a bit, just write if S belongs to this, or output read if S belongs to the other subset, else output okay, and the length of this string is going to be this much. Okay. Now, suppose this is possible. So, Alice and Bob knows the universe of cells in advance, they decide among themselves what to do, then Alice gets these two subsets, then Alice can send a string x to Bob, then using this string x Bob can build a data structure that can support these updates, okay, and the length of x is this. Then do we have a valid encoding? First, let us convince ourselves of that, and then we will see, then this just becomes a data structure problem, right? I mean, it can be solved using a hash function, those of you who are familiar with it. But first, let us just convince ourselves that this solves our problem. So, suppose there is one such protocol, then what Alice will do is, Alice will send the information transfer as before and this bit string x to Bob. Using this bit string, Bob has built now a data structure that can support these outputs. Now, using that data structure, how is Bob going to simulate what is happening in this interval? How is Bob going to simulate what is happening? In this interval, Bob is running many different threads. Okay? When one thread asks for writing or for updating a cell, then it is fine, right? Because to write a cell, it is not a problem. The problem is when you are reading a cell, whether you are reading the correct content or not. So, when a cell read operation is issued in any thread, Bob first checks that, okay, is this part of information transfer in that thread? Okay. If it is part of information transfer, we have the correct information. Okay. Otherwise, Bob asks that data structure. Now, let us see what happens. There are three cases. That cell from which now Bob wants to read either belongs here, or it belongs here, or it belongs outside. If it belongs here, the data structure will output write. Then Bob knows that, okay, this is a prohibited cell, because the accepting thread is not supposed to read this cell, and Bob will just terminate that thread. Otherwise, if it is here, it will output a read. Then Bob says that okay, it might potentially still be an accepting thread, and I am going to get the correct information if I read from here, right? Because otherwise it would have, what is the troublesome case where I am getting the wrong information? It's only when I am probing from this, and then I am sure that I am going to get back a right from the data structure. So, if the cell belongs to here, the Bob gets a read output from the data structure, and Bob goes ahead and reads the cell. Otherwise, the cell might belong here. Then there is some scope for error, right? I mean, it can just output anything arbitrarily, read or write. So, the protocol is when Bob gets the read output from the data structure, it will proceed and read the cell. When it gets a write output, it will just terminate the thread. Now, what is happening? If Bob wants to read some cell from here, it might still issue a potential read, right? Now, that is redundant because the accepting thread is not going to read from here, we know. But who cares? It is still getting the correct information because it was not updated during that slab T0, T1. So, we can proceed, right? And if it outputs a write here, then we are going to terminating the thread, and we are taking the right call because the accepting thread is not going to read from here. Okay. So, now you just think of it as a data structure exercise. How do you do this? Okay. So, all of the proof is finished barring this one lemma. Let me now just finish this lemma. It will take 5 more minutes. So, say lemma 4, and this will finish the proof. So, U is a universe S is a set with each element in this set we associate a bit (0, 1). This is either the read or write. Okay. And now we can build a data structure using, you can just map what is going on here, using order of S plus bits that answers okay. This is what we need, and now note that this is fine because order of S is going to be order of W plus R. What is log U? How much is U? U is some n to the power c, right? U is the number of cells, polynomial in n. So, log of U is basically log of n, and log of n is very small. So, here what would you get? You will just slightly need to modify this lemma, you will just get one additive log n term, right, if you apply this. And then will this lemma hold? Of course, right, because if you are summing over all the internal nodes, how many internal nodes you have? N. So, you just get one additive n log n term here, okay. And n log n is definitely much less than n log n. So, this will get absorbed in this thing, okay. So now the thing is, how can you do this? Okay. So this follows from the existence of a perfect hash function. So basically we need a hash function, say for example, let us say size of S is n, okay, and size of U is U. So now in the last 5 or 10 minutes I will just prove this lemma. This will conclude the proof. Okay. So what we will do is, we will build a hash function okay, and then at each entry we will store a bit. Now, if this is a perfect hash function on S, meaning that if you look at any two different values in S, then we can answer this query using this data structure, right, if we have such a hash function. Why? What will we do? When the data structure is probed for some entry in U, it will, suppose the data structure is asked, what is the data structure is queried at something, say x. So x belongs to U. The data structure is asked, return the entry, return the bit associated with x. So then the data structure can simply say that return the bit for h of x. Does this make sense? As long as no two s hash to the same value. Okay. So now the point is, let's just do it like this. How many different hash functions are there of this form? If you guys want to leave, then let me know. What we can do is we can just continue this next class. This is just one module. Do you have 10 more minutes? Then I can just finish this thing. Okay. So what is the number of different hash functions that satisfy this property? The number of different hash functions that satisfy this property is as follows. First, you need to pick the n entries where these different s values will hash to. You can do this in 2n choose n ways. Then there will be a permutation, right, between the set S and those particular n entries. So times n factorial. Then for the remaining entries u minus s, you need to decide where to hash them to. So how many guys are left there in u minus s? There are u minus n entries left in u minus s, and each of them can hash to 2n different values. So number of such hash functions that satisfy this property is this. Now if you pick one hash function uniformly at random out of all possible hash functions, what is the probability that h is going to be good? It is going to be this number divided by the total number of hash functions that exist. And what is the total number of hash functions that exist? 2n to the power u. Okay. And now this probability you can see is going to be at least 1 divided by 2 to the power order of n. Okay. This number. See, this n factorial will get cancelled by 2n to the power n. 2n to the power u will get cancelled by 2n to the power u, and 2n choose n. Okay, you can just check it out later that whether this is correct. Now, what you can do is, you just need to repeat this experiment many times. So, suppose H family of Now, is this going to be fine? If you do that, what is the probability that H is good with respect to one particular S? Then if you do that, probability that okay, instead of going there, instead of doing the calculation, let me just tell you the outline of the proof. What you can show is that if you pick these many uniformly random hash functions, then with high probability, not with high probability, with constant probability, the following event will hold. For every possible subset S, there is one hash function in this family that is good. Meaning, if you give me any S, so there are many possible choices of S, 2 to the power u choices of S. If you give me any S, I will be able to find one hash function in this family that is good. Okay. Then, what Alice needs to send Bob? Alice needs to not this family, the ID of that hash function. So, Alice and Bob can decide in advance an identifier for each of these hash functions in this family, okay? And then they know among themselves what each ID represents. Then how many bits will you need to represent one hash function from here? You just take the log of this, right? So, log of this is order of n plus log of, what is log of u choose n? Log of u choose n is n log u, right, because u choose n is u to the power n. So, this is now n log u, and what does this mean? Order of n plus log n. So, this is again order of n plus log u. This is fine, right? So, Alice will just send the unique identifier of this hash function, and then Alice will send a assignment of 0, 1 values to this range 1 to 2n, such that if you look at that specific S for which this hash function is good, the hashed values have the correct bits associated with them. Then Bob will just receive that string, and then just Bob can just implement that hash function. This is the end of the proof. Now, all you need to do is what I did not do very carefully, just check these two claims, and these are just two simple calculations that just so this will just follow from union bound, nothing else, and this is just one simple calculation to check. Okay.